At this point, you are probably very familiar with the normal distribution. You've learned that the normal distribution gives us probabilities on a curve that's shaped like a bell, where it's symmetrical about the center, and at the center is where we find the mean value. And you've probably also, up to this point, been working on a formula for calculating z-scores. Here I have the formula for calculating a test statistic on the normal distribution. So that test statistic is a z-score. To find it, you take your sample mean, subtract it from the population mean, divide it by the population standard deviation, divided by the sample size. When you start doing hypothesis tests in Chapter 8, you will have to figure out if you're going to approximate your probabilities with the normal distribution or with a new distribution that's called the t-distribution. So what is the t-distribution and how does it compare to the normal distribution? The t-distribution is very similar to the normal distribution, but obviously there are some differences. That's why we give it a different name. But basically, the t-distribution is used when you don't actually know what your population standard deviation is. What I mean by that is this. Anytime you're working with some statistical data where you don't know your population standard deviation, and the symbol that we use for population standard deviation is sigma. So anytime sigma is unknown, you always approximate your probabilities using the t-distribution. And you would use the t-distribution instead of the normal distribution, because if you take a look up at the top here, to use the normal distribution, we have to know sigma. So even if you're using the formula or if you're using normal CDF, so when you're using normal CDF on your calculator to calculate probabilities, you put in a lower limit, an upper limit, and then you put in your population mean, and then you type in your population standard deviation. But if your population standard deviation is unknown, then obviously we can't use the normal distribution. So if you take a look at the formula for calculating a critical value on the t-distribution, hopefully you can see that this formula is very similar to the formula on the left for calculating z-scores on the normal distribution. We still use our sample mean, see how far away it is from the population mean, but because sigma is unknown, notice in the denominator, we don't use sigma. Instead, we use S, where S represents the sample. So let me write this down in red. Okay, so S is your sample standard deviation. And then you divide that by the square root of n, which is your sample size. And so what this tells us is it tells us that the t-distribution is going to change every time you have a different sample standard deviation, so a different S value, and a different sample size, so a different n value. So this tells us that when we approximate with a t-distribution, it all depends on our sample data. And so the t-distribution, if you take a look on the left here, you'll see I have three curves. The curve that is in green is the standard normal distribution. Notice that the curve in red is the t-distribution, where your sample size is 12. And then the blue curve is also a t-distribution, but with a sample size of 3. And so hopefully you can see that these three distributions, the normal distribution and the t-distribution with different sample sizes, they all kind of have that bell-shaped curve, right? So they all follow that bell shape. But there are some significant differences. Notice that the smaller the sample size, right, when you're using the t-distribution, so look at that blue curve. Notice how much fatter the tail area is. So if I kind of highlight it in blue, I hope that you can see that the tail region on the t-distribution, when the sample size is relatively small, so a sample size of 3, the tails are kind of fat. So that means that the probabilities in those areas are going to be a little bit larger. If we compare that to the green curve, which is the standard normal distribution, hopefully you can see here that the area on the tail on the normal distribution is a little bit thinner. Okay, so the probability under that curve in the tail regions is a little bit smaller. But it turns out in statistics that as you increase the sample size, so as your sample size gets larger and larger, notice that that blue curve, right? compare that to this red curve where the sample size just went from 3 to 12, right? I hope that you can see that the tail starts to get thinner and thinner. So if you compare the red shaded region now to that blue shaded region, I hope you can see that the red shaded region is a little bit smaller than the blue shaded region. And in fact, it starts to get closer and closer to the green shaded region. So in general, if we can get our sample size to be large enough, right, the t distribution starts to be very, very close to the normal distribution. So when do you use the t distribution? You use the t distribution anytime that sigma is unknown. And so what you're going to use instead is your sample standard um, deviation and then your sample size n. And then that is going to help you determine the degrees of freedom. So the degrees of freedom is always used with the t distribution. And there's a formula for calculating the degrees of freedom when you just have one sample, and that formula is n minus 1. So that gives you your degrees of freedom to help you calculate your probabilities.